All right, so now we're going to look at some other techniques for evaluating limits, and we're going to continue with our discussion for evaluating limits using algebra and algebraic techniques. So we've talked about how for polynomials and for rational functions, direct substitution is most often applicable. There's some particular cases. Direct substitution is also applicable when we're dealing with a radical function, so long as in the case of an even root indice, if n is even, really you're looking at, is it defined for that radical? If that's the case, if you're looking at, for example, the limit as x approaches c of the nth root of x, if c is greater than 0 and n is even, then you can just directly substitute. You run into problems when you start dealing with your c value is negative, because of course you can't take the even root indice of a negative value. Okay, some other properties, limits hold under a composition of limits. So you can directly substitute a limit into a function. It holds under composition of limits. So if I want to define the limit as x approaches 0 of the square root of x squared plus 4, we can find the limit as x approaches 0 of x squared plus 4. That holds under direct substitution, that would equal 4. And so then finding the square root of, in this case, this is like my f of x. We found that limit as x approached 0, the limit of this f of x is equal to 4. So then we can conclude that the limit as x approaches 0 of the square root of x squared plus 4, you can just substitute. Essentially, you're just substituting 0 in recursively. Okay, and then similarly, looking at the limit as x approaches 3 of 2x squared minus 10, you would get that equals 8. And then the limit as x approaches 8 of the cube root of x is equal to 2. So you can recursively apply those direct substitution properties. You'd first input 3 in for x in the function 2x squared minus 10, and then you take the cube root of 8 and conclude that the limit as x approaches 3 for this given f of x is equal to 2. Okay, so you're recursively applying that direct substitution. Some general theorems for trigonometric functions. If your value of c is defined in your function, then direct substitution is possible for trig functions as well. Trig functions kind of fit the form and graphically of a polynomial, so the theorems run similarly. So for each one of these examples, of course, you can see we're just directly substituting the limit values in. In this first example, example A, we're looking at substituting 0 in. The tangent function is defined at 0, so that limit exists and it's equal to 0. For the second situation, we're just inputting pi. Both of these are defined at pi, and then we use that product property, the fact that products hold under limits, and with then direct substitution, we get that this limit is equal to negative pi. For C, we're using the power rule, that limits hold under powers, and then also that sine of x is defined at x equaling 0.